Hi! Welcome to my YouTube channel, Mom's Academic Learning, and today we're going to discuss the transformer on null load as part of AC apparatus course. Please don't forget to subscribe to my channel and hit the notification bell below. Let's get started. When we have an ideal transformer, meaning to say that we have no core losses and copper losses. However, in practical conditions, require that certain modifications be made in the foregoing theory. When an actual transformer is put on load, there is an iron loss in the core and copper loss in the windings, and these losses are not entirely negligible. Even when the transformer is on no load, the primary input current is not wholly reactive. Thus, the primary input current under no load condition has to supply these conditions. First, we have the iron losses in the core, which is made up of hysteresis loss and eddy current loss, and these losses are considered as the constant loss. And also, there is a very small amount of copper loss in the primary winding. However, since we have an open circuit, we have no copper loss in the secondary winding. Armed with this information, the no-load primary input current or I sub O is not at 90 degrees behind the input voltage but lags it by an angle of less than 90 degrees. Hence, no-load input power is equal to input voltage times the no-load primary input current times the cosine phi sub O, where cosine phi sub O is equal to the primary power factor under no-load conditions. The no-load condition of an actual transformer is shown vectorially in our figure. As you can see, the primary current I sub O has two components. The I sub W, or the active or working or iron loss component, and the I sub mu, which is the magnetizing component. By formula, the iron loss component, which is equal to I sub O times the power factor or the cosine phi sub O, and the magnetizing component, which is equal to I sub O times sine phi sub O. Obviously, I sub O is the vector sum of I sub W and I sub mu. Hence, we have I sub O square is equal to I sub mu square plus I sub W square. The following points should be noted carefully. First, the no-load primary current or I sub O is very small as compared to the full load primary current, and that is about 1% of the full load current. Second, the permeability of the core varies with the instantaneous value of the exciting current. When we say permeability, it is the ability of the material to create its internal magnetic field. Third, as I sub O is very small, the no-load primary copper loss is negligibly small, which means that no-load primary input is practically equal to the iron loss in the transformer. Lastly, as it is principally the core loss which is responsible for the shift in the current vector that creates an angle of phi sub O, and which is known as the hysteresis angle of advance. For our example 1A, a 2200 volts primary and 200 volts secondary transformer draws no load primary current of 0.6 ampere and absorbs 400 watts. Find the magnetizing and iron loss currents. So our given primary voltage, which is equal to 2200 volts, our secondary voltage, which is 200 volts. So as you can see, this is a step-down transformer. since the voltage has stepped down from 2200 volts to 200 volts. Then we also have the no load input current, which is 0.6 ampere, and the no load input power, which is equal to 400 watts. We are required to compute for the magnetizing and iron loss current. Okay guys, so let me share with you on how to solve problem number 1, letter A. So we are given the input voltage, which is equal to 2200 volts, the output voltage, which is equal to 200 volts, the input current, the primary input current on no load, which is 0.6 ampere, and the input power on no load, which is 400 watts. And we are asked to solve for the IW, which is the iron loss component, and the I sub mu, which is the magnetizing component of I sub O or I sub 0. So we can represent the components of I sub 0 or I sub O using the vector diagram. So this will be our I sub W, which is the iron loss component, and the I sub mu, which is the magnetizing component. And the resultant vector for that is I sub 0 or I sub O. So we can say that this angle pertains to our phi sub 0, or what we call the hysteresis angle of advance. So by, isn't it that we have a vertical angle here? So we can say that this angle is also equal to this angle. So let's say that this is also our phi sub 0. So if we're going to project I sub W into this side, we can say that this side is also our I sub W. Do you get it? And then we can form a right triangle. So we can redraw this figure. So we have I sub W, and on this side, okay, this leg or this base is our I sub mu. And this one is our phi sub 0, and our hypotenuse is our I sub O. So now we can solve for I sub W. But before we can solve for I sub W, let's have first the formula of W sub O, which is equal to V sub 1 times I sub 0 times cosine phi sub O. So W sub O is equal to 400 watts is equal to V sub 1, which is 2200 volts, times I sub O, which is 0.6, times cosine phi sub O. So therefore, from this, okay, the unknown is cosine phi sub O. We can compute for that. So cosine phi sub O is equal to 0.3030. And remember that cosine phi sub O is also equal to our power factor. Since we already have the cosine phi sub O, we can directly substitute this, okay, this value to our formula in computing for I sub W, which is equal to I sub 0 times cosine phi sub 0. So we already have the value of I sub 0, which is 0.6 ampere, times our cosine phi sub 0, which is 0.3030, and this is equal to 0.182 amperes. Okay. So we already have the value for our iron loss component, which is equal to 0.182 amperes. Now, let us solve for I sub mu. Looking back to our figure earlier, okay, so we can use the Pythagorean theorem or Pythagorean formula in solving for I sub mu. So I sub mu is equal to I sub mu square is equal to I sub O square minus I sub mu square. So this is equal to square root of I sub O square minus I sub mu square. And this is equal to square root of 0.6 square minus 0.182 square. And I sub mu is equal to 0.572 ampere. So we already have the value of I sub mu. For our problem 1B, a 2200 volts primary and 250 volts secondary transformer takes 0.5 ampere at a power factor of 0.3 on open circuit. Find the magnetizing and working components of no load primary current. Now we are given the primary voltage, which is 2200 volts, and a secondary voltage, which is 250 volts. Again, this is an example of a step-down transformer. And our no-load primary current is equal to 0.5 ampere and a power factor of 0.3. We are required to solve for the magnetizing and iron loss currents. Problem 1B is similar with our previous problem, which is problem 1A. And I'm going to leave that as your practice. Now, let us proceed to our next problem. For our example number 3, a single-phase transformer has 500 turns on the primary and 40 turns on the secondary winding. The mean length of the magnetic path in the iron core is 150 centimeters, and the joints are equivalent to an air gap of 0.1 millimeter. When a potential difference of 3000 volts is applied to the primary, maximum flux density is 1.2 Webers per meter square. Calculate letter A, the cross-sectional area of the core. Letter B, the no-load secondary voltage. Letter C, the no-load current drawn by the primary. And letter D, the power factor on no load. Given that the ampere turn per centimeter for a flux density of 1.2 Weber per meter square in iron to be 5, the corresponding iron loss to be 2 watt per kilogram at 50 Hz, and the density of the iron as 7.5 gram per cubic centimeter. We are given these parameters, and then we are required the following. Letter A, the area of the core. Letter B, the I sub O, or the input primary current. Letter C, the E sub 2. And letter D, the no-load power factor. Okay, so let us proceed to our last problem given the following parameters. We are now required to solve for the following. Letter A, the cross-sectional area of the core. Letter B, the no-load secondary voltage. Letter C, the no-load current drawn by the primary. And letter D, the power factor on no load. So, first, we are required to solve for the area of the core, and we can do that by having this formula. E sub 1 is equal to 4.44 times the frequency times the mutual flux times the number of turns in the primary. However, we are not given the mutual flux, but we can solve for the area of the core by having this formula, because we all know that the mutual flux is equal to the maximum flux density times the area. So substituting this to this equation, so we can have 4.44 times F times B times A times N sub 1. So therefore, we have 3000 volts is equal to 4.44 times 50 Hertz times our maximum flux density, which is 1.2 Weber per meter square, times the area, times the number of turns in the primary, which is 500. So in this case, we can solve now for the area, which is equal to 225 centimeter square. Now, let us solve letter B, which is we are asked to find the no-load secondary voltage. We know that the transformation ratio is equal to N sub 1 all over N sub 2, which is also equal to our induced EMF at the primary, which is equal to E sub 1 all over E sub 2. So, by having or by substituting the given parameters, so we have N sub 1, which is 500 turns all over 40, and this is equal to 3,000 all over E sub 2. So now we can solve for E sub 2 by having 3,000 times 40 divided by 500, and E sub 2 now is equal to 240 volts. To solve for letter C, which is the no-load primary current, first we have to get the total ampere turn for a given flux density. So how are we going to do that? So we have ampere turn per cm, which is 5 centimeters. Ampere turns per centimeters times the total length of the iron core, which is 150. So 5 times 150, so this is equal to 750. So this answer pertains for the ampere turn for the iron core. Now, let us solve for the ampere turn for the air gap. So this is equal to, for the ampere turn for the air gap, so this is equal to the magnetic field times the length of the air gap. And the magnetic field is equal to the maximum flux density all over the magnetic permeability at the free space. So B is equal to 1.2 Weber per meter square all over the magnetic permeability in free space, which is equal to 4 pi times 10 to the negative 7 times the length of the air gap, which is 0.1 millimeter, or that is equal to 0.0001 meter. Okay. So, the ampere turn for the air gap now is equal to 95.5. So, to get the total ampere turn, so we will just add 750 plus 95.5, and this is equal to 845.5. So this will be the total ampere turn for a given flux density. So to get the maximum value of magnetizing current drawn by the primary, so we have the maximum value of magnetizing current. So we have 845.5 divided by the total number of turns in the primary, which is 500, and this is equal to 1.691 ampere. But this is not yet the value of the magnetizing component that we want to get, because we have to get the RMS value, which is the effective value. So I mu RMS I mu is equal to 1.691 divided by square root of 2 to get the effective magnetizing component of the I sub O. And this is equal to 1.196 ampere. So this will be the value of our I sub mu. So we already obtained the value of I sub u, which is equal to 1.196 amperes. Now, let us proceed of getting the iron loss component of no load primary current I sub 0, which is I sub w. By getting the total iron loss, we are given that the iron loss per kilogram is equal to 2 watts per kilogram. So we want to remove this kilogram by solving first for the volume of the iron core and the total mass of the iron. So the volume would be the length times the area, which is 150 times 225 centimeter squared. This value was obtained with our previous solution in letter A. So 150 times 225, this is equal to 33,750 cubic centimeter. To get the total mass of the iron, so we have density is equal to mass all over the volume. So therefore, mass is equal to density times the volume. And density is given as 7.8 grams per cubic centimeter times 33,750 cubic centimeter, and this unit will be cancelled out. So our mass, total mass, is equal to, so let me get the calculator. So 7.8 times 33,750. So this is 263,250 grams. So we want to get the kilogram. So times, in 1 kilogram there are 1,000 grams. So this will cancel out. So 1, 2, 3. So we have 263.250 kilograms. Now we can solve for the total iron loss, which is equal to 263.250 kilograms times 2 watts per kilogram. Cancel. So this becomes 526.5 watts. So this will be our total iron loss. Okay, so we already have the values for I sub u and the total iron loss, which is 526.5 watts. Now we can solve for the working component, or the iron loss component, which is I sub W, which is equal to I sub O, or I sub 0 times cosine phi sub 0. But the problem is we do not have these three variables. Okay, so therefore we can use this formula W sub O, and W sub O stands for the input power at no load condition, and that is equal to V sub 1 times I sub O cosine V sub O. So do you see that I sub O cosine V sub O is equal to our I sub W. So therefore, we can substitute this, okay, to our equation. So we have W sub O is equal to V1 times I sub W. So I sub W is equal to our input power at no load condition all over our input voltage, and this is equal to 126.5 watts all over V1, which is 3000 volts. And that is equal to 0.176 amperes. So obviously, with our previous vector diagram, that I sub O is the vector sum of I sub W and I sub mu. Hence, we have I sub O is equal to square root of I sub W squared plus I sub mu squared. Substituting the values that we obtained previously, so we have 0.176 amperes square plus 1.196 amperes square. So this becomes, so we will get the value of I sub O, which is equal to 1.208 amperes. So to get the power factor, we all know that the power factor is equal to cosine phi sub 0 or sub O. So we can have the formula of I sub W is equal to I sub O times cosine phi times O. So substituting the values for I sub W, which is 0.176 amperes, and I sub O, which is 1.208, we can now solve for the power factor, and the power factor, which is cosine phi sub O, is equal to 0.1457. I would like to give special credits to B.L. Taraha and A.K. Taraha in using the textbook of Electrical Technology as my reference. Thank you and God bless. See you next time on my next video.